Segev talk about some application of differential geometry.
No. So, good morning, everybody. My talk is going to be somewhat theoretical, and I hope it will stir some of the excitement that we had after some of the talks of Francesco's talk and Gianpietro's talk. So it's not so boring. So I will start with controversy, and then I'll go to the technicalities, so maybe you won't be too tired. So I will start with the general conclusions of my talk. I'll start at the end, like some other people, and then I'll go forward.
That's for the supplementary.
So Gianpietro said that existence of stress is something which is distinct from balance. Did you say in a way? So I support this. I support this very much. And in fact, we are not going to have any balance here. So in my presentation, which considers the existence of stresses or hyperstresses, there will be no balance laws or balance assumptions and no principles. I have no principles. Okay? A man without principles and without balance also. Imbalanced person without principles. Maybe. We'll talk about this later. We'll get to this. This is a more technical point. So, and then Sepeshe mentioned also that mathematical technicalities have some significant physical consequences, which I also think is very important to realize, and maybe the rest of the more technical part of the presentation, I hope, will motivate that. So maybe what I will show in particular is that how the norm chosen on the space of virtual displacements in fact dictate what the interactions will be. Another thing related to these presentations was this question. Like this expression that people postulated as a starting point, you'll notice that some of the objection to this postulate that the virtual power for the velocity, say W, is of this form, was that these objects are not unique. So you can get the same results with the various different tensors, which we know from regular continuum mechanics. So if you have the virtual work, you know the virtual work for every velocity field, there are a number of, there's an infinite number of stress fields that will produce it, because the force, if you just talk about virtual power, does not determine the stress as long as you don't have constitutive relations. Okay, the statical problem is statically indeterminate in continuum mechanics. So still I will try to motivate this from a different point of view, so that the non-uniqueness of these terms, hyperstresses, is not so important. So, and the major, say, directions which I would like to follow is that once you define your virtual velocities, this implies what forces will you have, and then some mathematics will tell you what hyperstresses you have, and then, like the title of my talk, which Francesco did not want, oh, I forgot, I must thank the organizers, Francesco, and the local crew here, and I think we should, very warm welcome, and very nice, I was excited, so I forgot to say it at the beginning. So thank you. And then this will, I will talk about optimization. Now, all this was very abstract and whatever. So I want to motivate this abstract setting by some practical result. Practical result. So what do we do as engineers when we do stress analysis? I mean, we're engineers, right? So we have a structure. We are given the geometry of the structure, and we postulate these or write the equations of equilibrium. However, the stress field, I'm talking about regular continuum mechanics now, right? So the stress field is sigma. You know, it is not unique. The system is underdetermined, statically indeterminate. We have 6 independent stress components, only 3 equations. Then we use constitutive relations to rate the stress and the kinematics. And then hopefully we get some solution. Hopefully it's unique. And then we use some failure criterion to measure what the sum function. This is the failure criterion function of the stress. Okay, I wrote some tau here is the stress matrix. Is it smaller than some permitted value? And we check whether the maximum of the stress, whether this supremum over all points is indeed smaller than the permitted stress, and then we are happy and we get our paycheck by the end of the month. Is that more or less? Yeah. So to show you some of the, say, practical aspect of what I wanted to present, I want to show you this result. So we have omega here is a given region. We know the geometry, and we assume that we are talking about a structure which is elastic or may not be linearly elastic, but most importantly, it's perfectly plastic. It's perfectly plastic, which is important. So it's perfectly plastic, and Sy is the yield stress. And T will denote a loading, some loading traction on the body. Some loading traction on the body, and the idea is that as engineers, we don't know exactly what forces are going to act on our structure, right? So Tmax would denote the maximum of the applied load, so the maximum of the norm over all points on the boundary of the applied load. So this result says that there is a maximal number C, that the body, I can assure you, I can grant you that your body will not plastically collapse, will not collapse plastically, as long as the maximum of the applied load is not larger than this number C times the yield stress. And this is independent of the distribution of the external traction. So you give me the geometry of the body, I put it in my machine, I calculate, I get the number C here, and I know that as long as your applied load, and no matter how it is distributed, is not larger than C times the yield stress, your body will not turn into a mechanism. So, and to show you that this thing is this is an example, this is an example, a calculation that a student of mine has made. So you have, this is the structure, this is these are finite elements, it is like a dam, and it has a crack here. Down here it has a crack. And just by doing geometric calculations, I am able, for example, to determine the worst case loading. So this is the worst case loading. So you can see that the force here is almost vertical because it wants to open the crack, and over there at the top it's almost horizontal because it wants to bend the dam. And this is a result of the analysis. If we go back to this load capacity ratio, this number C, as I mentioned, it's a purely geometric property of your domain, omega, and it is given by this formula. So what you do, you take all velocity fields or vector fields on omega, you integrate them over the magnitude over the boundary, you divide by the integral over of the strain over the volume, you take the supremum of this is 1 over C. And not only that, just so mathematicians also enjoy this talk, if they do. So this number, 1 over C, is nothing else but what is the norm of the trace mapping of the right Sobolev spaces. So this number, which has very good, some mechanical significance, is nothing but the norm of the trace mapping. The mapping that takes field on omega and gives you the boundary values from the point of view of functional analysis. So I explained this more or less. So as the title of my talk mentioned, I'm going to talk about optimal stresses. So what are optimal stresses? The mathematical problem of optimal stresses is what leads to this notion of load capacity ratio. I will not get to plasticity or load capacity ratio in this talk, but I just wanted to motivate because it's the same analysis. Just you continue 2 more lines and a few more lines and you get this load capacity ratio, but I will not get to that. But a related notion, which I hope I can present here today, is that of optimal stress field. So the question is as follows. You have the geometry. You have the geometry of the body, and you know the applied load. And what estimates or bounds apply to the stress field on the basis of equilibrium alone. So I don't have any constitutive relations. I just have the geometry, I have the loads, and I have the class of all equilibrating stress fields that equilibrate this known load. And the question is then, what can I say about some bounds that apply to these stress fields? So this problem has been studied since Signorini, Grioli, Truesdell and Tupin Day in 1979, and they all gave lower bounds on the maximal stress in terms of the applied load only. So the maximum of the stress of over all components and all points x give you should be greater or equal to a bound which depends, of course, on the force distribution T. However, these bounds that they give are not exact. They are not exact. So the question arises, what is the greatest lower bound of these maximal stress components? Another question, a more mathematical, formal question. Okay, say you found this greatest lower bounds, but is there an actual stress field for which this bound is attained? And so this is a question, and just an observation that a stress field for which the bound is attained is optimal, because it means that you found a stress field which equilibrates your external loading, whose maximum is the least possible, so that equilibrium is valid, holds. So this is the notion of optimal stress field, and this is actually a large part of the talk, and I hope you appreciate the question. So you see why it's significant. We ask sometimes students to do such problems with the trusses and stuff like that.
Just a question.
Yeah?
Constitutive assumption is completely irrelevant.
Exactly.
And you could also give this nonlinearity, or is it now the calculations you are coming is based on the reference configuration to somehow linearize?
Since I don't, this is not tied to the kinematics via constitutive relation, I'm talking now about the region. So, in fact, I'm talking about the, say you can call it the current configuration. Okay? So, actually, I can give you already the result for the case of hyperstresses. So, let your hyperstress be composed of sigma I, sigma jk, etc., up to the sigma, say, with rs, whatever, up to z, the hyperstress field, such that for each field, velocity field, this holds. Francesco will immediately jump and say, what about edge interactions? So let's say we don't have edges for today. Okay? You will Forgive me. So we don't have edges here, and we have this
External edges.
pardon me? External edges, yeah. Okay, yeah. And also I'm allowed, this is my talk. So, here we have the expression for what they call the internal virtual work, external virtual work, and then I say that the optimal stress is given as follows. So this is the definition. This optimal value is the essential supremum over I forgot to have the minimum here, the infimum here. So I take the infimum of this thing, you see. I take the all points in the body. I take all components of the stress, of the hyperstress. I take their magnitude, and I take the essential supremum. And I want this to be, I forgot to write here, the infimum of this over all stress fields that equilibrate the external loading. Okay, so I want this to be minimum. That's what I call the optimal stress. And the result is that this thing is the following. You calculate the virtual work here for all smooth velocity fields, and you divide it by the sum of the integral of the absolute value of the components of the stress or of the velocity field up to all the partial derivatives. That's in the denominator, all the partial derivatives.
So the omega is converged.
Pardon me? Comma is here. Comma is the differential, partial differentiation.
Omega, it is compact in yours.
No, it's on omega.
Well, omega is
Omega.
bounded.
Omega is bounded.
It's bounded.
Omega is bounded. It's open, but it's bounded. And let's say it has a smooth boundary for today. So, and also the optimum is attained for some optimal stress. And another nice mathematical property for the mathematician is that this optimal stress is nothing but the norm of the force functional or power functional, whatever you would like to call it. So this I think is I like it.
Sorry, what would be in which norm, in which space you are?
Well, I'll explain this in a minute, but you can see here, it says here that you can take all smooth fields in omega, and this is exactly, you take the absolute value of all omega I, integrate them over omega, and then omega I comma j, integrate the absolute value of over omega, and you add up, and the formalities will come later. Okay? So some notation. That's, do you have some, maybe this. What do I press? Here? Yeah. So Rn, say, represents the tangent space to the Euclidean space where we work. Omega, a bound and open subset of Rn, having, say, a smooth boundary which represents the body. So omega is your body. A velocity field is a mapping that takes the body into Rn. And this is very important. This is what is called the jet space. So the jet space contains values of components of W, and also gradient of W, and also higher gradient. The higher gradient are linear, k times multilinear actually, symmetric mappings of Rn into Rn. So Jk contains all possible partial derivatives, values of partial derivatives of a vector field up to order k. I hope, and I use a multi-index notation. So alpha tells you it's a sequence of actually n, it should be n here, n numbers that tell you how many times you differentiated with respect to the, say, ith coordinate. So alpha I, for example, tells you how many xi appear in your differentiation. So, and then you have what it's the jet extension or jet prolongation mapping. And the jet prolongation mapping of omega it takes your velocity and gives you a function on omega, on the body, that gives you all the components of the partial derivatives up to order k. Okay? So this jk simply gives you all the partial derivatives of various orders up to order k. So you can, if you're talking about continuously differentiable mappings, k times. So if you have k times continuously differentiable vector fields, jk takes them and give you continuous mappings into the jet space, because the last component is only continuously differentiable. Okay, so this is just the notation. So remember, this is the differential operator, and this is where the values of the differential operator live. So we have, let's say we have any measurable mapping chi. Now chi is supposed to represent a field of this jet. That is, at each point you get a vector field, something which is a linear mapping, and symmetric multilinear mappings, but they need not be compatible. So such a mapping chi here is a collection of tensor fields which need not be the derivatives or the gradients of one particular velocity field. They're not necessarily compatible vector field, tensor fields here. So we want to say that such a chi is LP. If you can, if when raised to the power p, all the components, and then you integrate over. Actually, the sum should be on the outside of the integral. You integrate each of them over the body, and then you take the sum of them of this. The sum should be outside of the integral, and then you take the pth root. We call this the LP norm of your chi. This way, LP of omega and this valued in the jet space is a Banach space of LP fields with this norm, and we look at them as maybe internal virtual velocities or local virtual velocity, depending on your taste, the way we would like to call them. So this is a way to think about them. Of course, we have for LP, we have the dual space, and we have the dual power p prime, so that 1 over p plus 1 over p prime equals 1, or p prime is equal is given in terms of p this way. And in case p equals 1, p prime, as probably you know, is infinity. So the dual space of the space of LP vector tensor fields is LP prime, and each such functional, each of these elements is a functional, and it is represented by means of such fields of LP prime fields in this form. Yeah, we just multiply and integrate and add up on all components. So this is the space of LP, say, jet fields, and its dual. We also have what is the space of the Sobolev space of PK fields. So these are vector fields on the body whose jet extension, jet prolongation, that is the field and all its gradients, all of them are in LP, and this is the Sobolev space of vector fields. It's a Banach space, and you define a norm on it as follows. You say that the norm, the LP norm of W, the norm here, is nothing but the P norm of the jet of W. So you take all the derivatives. 5 minutes. Okay. I will not finish anyhow, so it's okay. So, and you take the P norm for these. These are global virtual velocities. That's how you should think about them. So as a conclusion, we see that this mapping, JK, takes these Sobolev vector fields, give you LP tensor fields, is, first of all, it's linear. It's 1-to-1 because if you take the the jet of a vector field, it includes the vector field itself. Where was it? Here. It contains the vector field itself, so it must be one-to-one. And it preserves the metric because of this definition of norm on the Sobolev space preserves the norm, so it's also isometric. So now we can state what we conceive as a force. A force is a linear and continuous functional on the space of these velocity fields. The Sobolev space of velocity fields. Actually, the particular case I'll be interested in is P equals 1. P equals 1. And so this would be a force, or maybe a WPK force. And the action of the force on a virtual displacement is the power functional, or it's the virtual power performed by the force F for the velocity W. What is a stress? A stress in general is an element in the dual of this space, of the LP fields. And as such, it can be represented as follows. This is by LP theory. So a stress acts on a non-compatible field in this form that I wrote also before. And you think about this, say, as the local or internal virtual power. So probably I should stop with this theorem, and then I will end up my talk, at least for. So it is a result of a mathematical representation theorem. From this definition of a force, it's the result of mathematical standard procedure that any force is represented in this form by a collection of stresses. So the force object is uniquely defined, and it is a result that it is represented in terms of hyperstresses in this form. And actually this relation can be written also as this. That is the so-called equilibrium operator is nothing but the dual of the jet mapping, of this jet mapping jet extension. And this actually is what we would like to call the equilibrium equation, but there's no assumption, no equilibrium, and no balance, no nothing. And the proof, which I mentioned is standard, is based on Hahn-Banach theorem, which is kind of technical, and that's the sort of nice thing about it, what I referred to before. The technical aspects of the mathematics are relevant to mechanics. Not only that, but we know that it's non-unique. So if you have the force, the stresses representing the force are not unique, and this follows from the non-unique extension of the Hahn-Banach theorem. So everything is sort of all the physics that we would like to represent is contained in this formal mathematic framework, and the idea of optimal stresses follows also because by the Hahn-Banach theorem you can extend the linear functional without increasing its norm. And this is a crucial point, which of course I won't have time to say. So with this I will end. Thank you very much.
About the problem that Francesco raised of the uniqueness of the optimal stress.
Yeah, I don't remember what.
Uniqueness of the optimal stress.
It's not. Did I say it was unique? Did you? I don't remember that you asked this, but I do not. I didn't say it is unique.
Yes, you defined it in some way.
I defined it, but I didn't say that there is a unique stress field that is optimal.
No.
The existence of an optimal stress, but I did not say. And if I said I'm sorry, I didn't mean to say that the optimal stress field is unique. I didn't mean to say that.
By usually limit analysis,
Exactly.
is applied to proportional.
Exactly.
and the multiplier is supposed to be unique. The limit multiplier.
The multiplier is unique, but the stress field is not unique, as you would agree, right?
But my point is that in fact this multiplier is not unique. So there is a beautiful paper by Massimiliano Lucchesi and Mirko Shintani who proves that this multiplier depends upon the extent of the space of the Newton displacements.
Okay, exactly. So in this space, I get this result. Well, I will agree to that, because actually, if I can go some more, so it.
I was not reaching up.
You see, well, here instead of L1, I could choose other spaces. I will get different. It depends on the definition of what. I agree. Yeah.
And you should point out this when you speak of that, because people are used to think that the multiplier is unique, and it is not.
Okay. It depends on, for example, also on the norm that you choose for your external fields.
Yeah.
Okay. Yeah. Okay. Sure.
I have just a comment on this representation of the theorem.
Yeah.
I strongly agree with you. In my PhD thesis, I also developed in some way a similar approach. And what I want to remark is a possible criticism that I also made myself
Okay.
at that time, is that so when you have this very general framework of finite manifolds and those jets, you can also consider, let's say, systems where you have generalized velocities of different kinds.
Yeah.
Also, different order. You may have something which is a third gradient in something
Okay.
and also sub-manifolds. So the possible criticism is that in this way we are saying basically that a generalized continuum is everything that can be described with differential equations. Because it's
What's the general. It's very general. It's
It's not even enough.
yeah. So yeah, it could be integral differential equation. I don't see why it's criticism.
well, I'm not saying that it's a bad thing. I also like this approach, but then we need something else to decide what kind of.
Of course, I didn't say that this tells you what your continuum is. You have to decide on your class of your configuration space, what rank you take, what high hyper is your hyperstresses are going to be, or what kind of jets you take, and what is your configuration space, say, for the internal variables, and you have to choose them according to the physics that you want to describe. It allows you to make this choice. It's a good thing.
As I said,
Last question.
Short question. Using some duality ideas, I guess that it is possible also to do the same bounds, similar bounds for strains.
Well, of course, you can.
Because in some sense it's dual.
It's dual.
And obtain, for example, such equation, answer for such equation. We know some kind of limited displacement of the surface of body. Then we can estimate the strain inside.
Given the forces, you have to know something. Oh, but that's the. I think that may be the Sobolev embedding theorems. They may give.